Dear ladies and gentlemen, welcome to my presentation. In the following minutes, I will give you some insights about the topic of our paper, Best Practice-Based Framework for User-Centric Privacy-Preserving Solutions in Smart Home Environments. First of all, I will give you a short introduction to our topic, insight to our proposed framework. Then I will come to the qualitative evaluation of our approach regarding functional and non-functional requirements, and will close the presentation with discussion, conclusion, and future work. Now, coming to the introduction, the technological progress in the context of pervasive systems leads to the fact that more and more smart objects are integrated into our personal spaces, such as homes. The integrated smart objects in such smart home environments are, for instance, smart bulbs, fridge, door locks, etc. Although these smart objects improve our lives, they also collect and disclose a vast amount of sensitive and non-sensitive data without users' consent. Especially in smart home environments, this privacy issue gains more importance because the integrated smart objects in smart homes collect data in a personal space. In order to address the rise in privacy issues in this context, several privacy-preserving solutions, including different machine learning and automated approaches, have been proposed. Note that most of them do not allow the entire control over the data collection, storage, and disclosure process, and also do not supply users with data disclosure recommendations based on best practices, context-sensitive factors, and users' past activities. European General Data Protection Regulation, called GDPR, with different articles and existing works, are still calling for privacy-preserving solutions with more user centricity and possibility to consider context-aware user privacy preferences. The proposed framework for user-centric privacy-preserving approach in this paper delivers user data disclosure recommendations while considering GDPR-based best practices, user context-aware sensitive factors, and privacy preferences from past activities with minimum human interference. In order to allow users to control the entire data collection, storage, and disclosure, and to integrate into existing IoT architecture systems, the proposed framework is integrated within an existing user-centric privacy-preserving approach, which was published in the Ubiquitous 2021. On the right, we can see the existing approach in which we propose to integrate the presented framework. To give you short explanation regarding the existing approach, it includes 4 UCCPs, so-called user-centric control points, and allow users to minimize, aggregate the collected data, and limit the access of the shared data by limiting the data consumers and usage purposes. Mentioning that, I would like to present you our proposed framework in this paper briefly. The proposed framework consists of pre- and real-time processing as shown on the right, and it includes different inputs, such as collected data in smart homes, initial best practice trained data, and 2 machine learning algorithms, supervised learning including decision tree, and active learning including support vector machines, SVM. On the next slide, I will give you a bit details regarding the initial best practice trained data. First of all, let us have a look at the mechanism of the proposed framework. In the pre-processing, the first training iteration is executed, and for this, the initial best practice trained data is used to train the recommendation manager, and in the first iteration, the data of the initial input data and the individualized best practice trained data contain the same data. After the first iteration, the automated solution can be applied in any smart home environment defined as real-time processing. After the application of the framework in a smart home environment, the recommendation manager supplies users with data sharing recommendations after the collected data types in that respective smart home environment are imported to the model. In case the users decide to adjust the recommendations, then 2 variables of the initial best practice trained data, called sharing classification and sensitivity level, are adjusted, and those adjustments are included in the individualized best practice trained data for the next iteration. The sharing classification is adapted according to user settings, and the values can be changed between 1 and 0. 1 for share the data, 0 do not share the data. The sensitivity level is adjusted according to the following procedure. At first, users are asked to indicate their perception regarding the dependencies between the collected data types, and the users are also supplied with information icon with backgrounds details for each collected data type. An example for this is biometrical data such as fingerprints, voice prints, face IDs describe specific characteristics of a natural human. They are only asked to indicate dependencies for a small sample of the collected data, and based on the user's inputs, the SVM defined the dependencies for the unlabeled data. When indicating the dependencies for a data sample, the users are also asked to set a weight coefficient between 0, dependency is weak, to 1, dependency is strong, for the indicated dependency. Once the users decide to share an assigned data type, for example fingerprint, twice in a row, which leads to the interpretation that the user does it deliberately, then the sensitivity level of the dependent data types will increase. In order to adjust the sensitivity level of the dependent data in the proposed framework, the proportional integral derivative PID controller is used, a widely used control system in the industrial world and a variety of applications. On the next slide, I will give you details regarding the PID adaptation in the proposed framework. After explaining the mechanism of the proposed framework on this slide, I would like to give you some insights regarding the initial best practice training data and the PID control applied in the proposed framework to adjust the sensitivity level according to users' data sharing preferences. Starting with the initial best practice train data, in order to train the algorithm of the proposed framework to supply users with data disclosure recommendations, the initial best practice trained data is derived and used for supervised learning. The initial trained data includes different variables such as the collected data types, the corresponding smart home object, collecting the data type, sensitivity level of the respective data types, sharing classification for that respective data type, and few user details such as age, user category, and country. These variables are considered because they influence the sensitivity perception and which then in turn influence users' privacy and data sharing attitude. The figure on the right top presents an extract of the initial best practice train data. Coming to the PID controller, the figure on the right bottom presents how we apply the PID controller in our framework. The technique of the PID controller includes the calculation of an error value, which is the difference between the expected set point called as P and a measured process variable called PV. In our approach, the set point of a dependent data type is twice of weight coefficient of set point of a dependent data type, and measured process variable is set to corresponding weight coefficient of the dependent data type. In every iteration, the users decide to disclose a specific data type. The weight coefficient of the dependent data type will incrementally increase according to the set value of weight coefficient of the dependent data type. In case the error value is greater than or equal 0, the sensitivity level of the dependent data type increases by 1 can be increased to 10 with highly sensitive. When the users decide to disclose dependent data which has already been increased in sensitivity level, they are explicitly asked whether they are sure about this decision because of the already shared data in the past. Increasing the sensitivity level of a data type will always cause the sharing classification to be set 0, do not share, if this is not the case. Integrating these mechanisms helps to consider users' past activities and contain sensitive perceptions while supplying them with data disclosure recommendations according to their privacy preferences. After describing you the proposed framework, let's have a short look at the modified user-centric privacy-preserving approach after integrating the proposed framework. The integration of the proposed approach simplifies the previous privacy-preserving approach and only contains two UCCPs. UCCP1 data aggregation and UCCP2 data sharing and access limitations. The differences comparing to the former user-centric approach is that in UCCP1, additional user inputs such as user details and category are asked as input, and users are also asked to indicate their dependency perceptions between the collected data type for a small sample of data. Therefore, this SVM is also applied in order to generate the output for the UCCP2, which is the dependencies and weight coefficients. In UCCP2, we integrate the proposed framework and the output from UCCP1. Based on the learning algorithm and the mechanism, the data sharing recommendations are supplied to users. In case users decide not to follow the data sharing recommendations supplied based on the framework, then the users are asked to set the data consumers and usage purposes. At this point, the user preferences will be captured and used to update the two variables in the individualized best practice trained data, which are sharing classification and sensitivity level according to the mechanism of our proposed framework as described on the previous slide. Furthermore, users can also access the shared data with data consumers for different usage purposes. They can also disclose those already shared data with further data consumers for other usage purposes. To sum up, the integration of the proposed approach in the existing approach allows supplying users with data sharing recommendations with minimum human interference while considering users' past activities and context sensitive preferences. Moreover, integrating the proposed framework allows users to control the entire data collection, storage, disclosure process in smart home environments. After looking at the UCCPs, in our paper we also evaluated the proposed approach qualitatively, since the implementation of the framework is not part of this manuscript. In non-functional evaluation, we consider different security, privacy, and performance-related requirements. To summarize the evaluation results in this area briefly, the modified privacy-preserving approach is implemented in the DSP and server element, which allow to run the machine learning approaches of the proposed framework. Due to the consideration of less time, cost, and energy-consuming machine learning methods and their integration in a server-based DSPM allow us to deliver results fast within 250 milliseconds on the user interface, which is a reference value for delivering results on a user interface according to Reskin. After the initial installation, the updates are installed automatically, and the approach allows collecting and processing the collected data in a privacy-preserving way according to GDPR requirements. The collected and processed data can be accessed via a mobile application, and it only allows minimum number of external access to allow control of the entire data collection, storage, and disclosure process. The approach can be implemented with the Java-based tool called Wicca to improve the portability and deployment flexibility. All the collected data are integrated in the modified approach implemented in the DSPN of the IoT architecture systems, and the capacity of the DSPN can be expanded with upgrades. Additionally, the approach is integrated in a high availability server element, which causes at most 5 minutes of service interruption per year. And in case the DSPN server element is down, the data of the DSPN can be accessed on a private cloud, which is installed in one's smart home environment. To sum up, the evaluation outlines that considering the above-mentioned requirements in the proposed framework allows fulfilling non-functional requirements from security, privacy, and performance-related categories. We also evaluated the proposed approach concerning the functional requirements qualitatively. For the evaluation, we chose 4 existing approaches which are relevant works in this area and provide the basis for our work. While Keshavarz and Anwar in the both works proposed standalone machine learning approach allowing users to express their data sharing and data sensitivity preferences by labeling a sample of collected data, Kunudus et al. Presents a technique to present users derived conclusions based on collected data about users' daily routines and activities. Additionally, Ivodier et al. Presents an architecture allowing users to understand and control their smart home network. The evaluation matrix are organized in 3 categories: privacy-preserving features, user-friendliness, and GDPR requirements for automated decision-making according to Article 22 of the proposed solution. However, the detailed and qualitative evaluation of the previous solutions outline that those approaches do not supply users with best practice-based data sharing recommendations with minimum human interference while considering context-sensitive factors and users' preferences based on past activities. Furthermore, integrating the proposed framework in an existing user-centric privacy-preserving approach allows users to control the entire data collection, storage, and disclosure process and integrate the proposed solution in existing IoT architecture systems. Coming to the discussion and related work, the proposed framework allows addressing existing gaps and demands from GDPR, especially from Article 9, 12, 15, 17, and 19 and 22, in context-aware privacy-preserving preference modeling research. The proposed best practice-based framework for user-centric privacy-preserving approaches in the smart home context supplies users with data sharing recommendations while considering context-sensitive factors and user preferences based on users' past activities. However, the initial input trained data must be validated based on interviews with GDPR experts, and further investigation within a user study must be carried out to find a user-friendly way to capture users' dependency perceptions and validate the predefined inputs. Finally, our work has few limitations. The findings are mainly based on a literature review and on a previous proposed approach. Our derived approach must be validated with user studies in a real-world experiment. Having a brief look at the related work. The existing works can be clustered into categories: technical solutions for disclosure behavior prediction in different contexts, and machine learning solution in IoT and smart environments. The works from those categories present different solutions in different contexts, for example, location sharing systems and smart environments, for categorizing between sensitive and non-sensitive data and general data labeling, etc. However, the contribution of the proposed approach to this body of literature is threefold. Best practice-based frameworks supplying users data disclosure recommendations while considering context-sensitive factors, user preference in data sharing recommendations after learning from users' past activities, and its integration in an existing solutions allow user to control the entire data storage, collection, and disclosure process with minimum human interference. Furthermore, the entire proposed approach in this paper allows addressing a few existing gaps in context-aware privacy preference modeling with user focus as mentioned in the previous works. With that, I would like to come to the conclusion and future work. To sum up, in this paper, a best practice-based automated framework is proposed, which supplies users with data sharing recommendations based on GDPR-related best practices and allows to consider users' past activities, privacy preferences, and context-sensitive factors. Integrating the proposed approach in an existing user-centric privacy-preserving approach allows users to control the entire data collection, storage, and disclosure process with minimum human interference. Furthermore, this integration also allows us to implement the proposed automated approach in existing IoT architecture systems. In future, we plan two core points: to implement the proposed approach in a real-world smart home environment, and to conduct user studies to investigate the performance and user acceptance. This was my presentation about our paper, and thank you very much for your attention.